Trash.
I'm watching.
Nope, I have something more important.
Oh, did you
Trash,
try
you
it?
were so right, dude. Banger, bro.
Dude, they're good. They're
Absolute
good.
banger.
My favorites are the red and the pink.
Red.
So
Oh.
obviously, you
Delicious.
should listen to Trash when it comes to snacks.
Like the first time I ate it, like I ate a red one, and my eyes like rolled to the back of my head. I was like, I can't believe.
I'm sorry. What were the name of those treats?
I thought it was a
Yum
dog
Earth.
treat.
Dog treats.
I was thinking they were dog treats.
Yeah, it says Chewy on it.
They
I'm like,
kinda-
that's a
they
dog
Yeah,
kinda
treat.
come
Chewy's
in a bag.
that's a dog brand, isn't it?
It is. This is
Chewy.
Chewy's.
By
Yeah,
Yum
but
Earth.
Chewy.com is a dog food
Yeah,
site.
it's like
You're
the
right about
subscription thing.
Yeah.
It does say allergy friendly. The more I read the packaging, I'm wondering, have I been eating dog treats for the past day? They're delicious.
Anyways, sorry. All right, welcome to the stand-up. Today we have with us Ginger Bill, an actual quantum physicist, Tej, and Trash Dev, and we're going to be talking about things quantum AI because, you know, I don't know about you guys, but every single week I see some breakthrough quantum computer is going to be absolutely amazing, and this week Google released a paper showing that it's able to do verifiable quantum algorithms, getting reproducible results through, and it's finally time. AI supremacy or quantum supremacy, maybe quantum AI supremacy
It's
is going to
from
happen.
Google Quantum AI, so
It's gonna happen. We're gonna see it, and since none of us are smart enough, except for Ginger Bill, to actually understand what's happening, we thought we would discuss this and bring on a real semi-expert.
Quasi-expert.
I thought we were talking about semi-trucks.
It's to lay the foundation. This week, Google released a paper along with the marketing video showing that they've created something called quantum echoes, effectively a way for them to be able to take some sort of chip with 105 qubits on it, do some sort of perturbation is what they call it, make it vibrate, and then run the algorithm in reverse, and boom, they're sucking out answers with pretty high reproducibility and able to actually predict structures of molecules and all that. Now, for us, what does that actually mean? Is there any actual practical implication? Is 21 still the largest factored number by quantum machinery? We will find out. All right, Ginger Bill, since all of us are actual online idiots, can you just please give us like the
Professional online idiots
Professional,
to you,
yes.
sir.
Sorry, I'm paid, so I'm not an amateur like
Hey,
Trash.
professional, an amateur. It's fine.
I'm a professional here.
I had a couple dollars.
That's true. We made a couple dollars, deleted a couple posts, not a big deal.
Oh no! Oh no!
Could you please give us like the high level of quantum computers, what this actually means, like something to kind of help us as idiots understand all these sensational articles we see constantly?
Right. I'm going to try my best here to explain any of this. Okay, so most people, okay, I'm assuming the audience here knows at least the basics of computers, right?
They probably know quantum slit test as well, the double whatever.
gotta work
So
our
I'm going to
way
ignore
there.
all that. I'm going to go even more simpler first, just to break it down. You've got classical computers, right? Let's call it classical, right? This is where you've got, let's say, binary
Mozart,
computers.
Beethoven.
Yeah,
right?
yeah, all those stuff
That's where
like
I was
that.
going.
I was a
Classics,
Bach
Tchaikovsky.
man myself, but yes, do like it in sonata and C minor. Ooh. Now we're going from there. Classical computers, in like we've got binary things. You've got like ones and zeros everywhere. Well, we call these bits, right? A bit, it can store two states, either 0 or 1. If you've got 2 bits, you can store 4 states: 0, 0, 1, 1, 0, 1, and 1, 0, right? I don't know why I did it in that order, but you can see what it gets. And you get to 3 bits, you get 8, and you can see how many different states you get. Now, the thing is, in classical computers, when you've got something with that many bits, it's either in one of the states only, right? If there are 3 bits, it can be only in one of the 8. That's it.
Did you find the errors?
I don't even know what they look. What do they even look like?
They're in the phone.
In the phone?
Yeah, they're definitely in there. I just don't know how we labeled them.
I got it, don't worry.
You gotta
Gotta figure it out. We're running out of time, Prime. You gotta find them and meet me at the stand-up.
Roger.
They're in the phone. It's so simple.
Get all the context you need to debug your problem, because code breaks, so fix it faster with Sentry.
Right, that's the simple bit about, and then basic classical computers, you've got bits. Now, when you get to quantum mechanics, they have something fancier. They like calling them qubits or quantum bits. And what they do here is, I'm going to say a fancy word which isn't actually that fancy at all when you actually understand it, is they say a qubit is something that is a superposition of both the 0 value and the 1 value. Now, the word superposition really confuses most people because it's just sounds silly. But most people probably understand what it is. The one you always, like the textbook one you learn in physics is like waves, right? If you can think of imagine it's an extremely still pond, right? And you dropped like 2 stones at different parts of the pond, they'll produce ripples, right? When the ripples come to interact with each other, right, you've got 2 sets of waves coming to interact. How those waves interact with each other, add together to make one new wave, that's called a superposition of 2 different waves. That's it. That's all it means. You've added, literally they've come together, and that's a superposition. Now, the more abstract thing is when you're talking about these qubit things, is that they are now superpositions of the 0 and a 1 state, or whatever they correlate to. So in this case, it's a little bit more like, hey, this thing, this qubit, it's like, let's say there's a 40% chance it's in the 0% state and a 60% chance it's in the 1 state, right? But that's its like state currently. That's the state of that qubit. I'm going to make it completely static here as well, not to confuse anyone further. So you've got a basic idea of what a qubit is. Now, the funny bit is when you have 2 qubits, right? Let's make it a little bit more fancy. Again, before when we had 2 bits, we have these 4 possible states. But when you have 2 qubits, you usually want to entangle them together. Now, this word entanglement is
like
effectively
in
just
the
intrinsically
Avengers.
linked. You can't pull them apart. Yeah.
Okay, hold on. I need to know, is TJ correct? Is it entanglement like the Avengers?
I actually haven't watched
Neither
any of the
Adventures,
movies.
neither the spy one or the superheroes
What about
one,
like Love is
unfortunately
Blind
not.
entanglements? Like, what kind of entanglements are we talking about here?
Is
Oh.
Interstellar a documentary?
I'm sorry to tell you, Tej. It's a film by Christopher Nolan.
He makes my favorite documentaries.
I know, they're really sometimes good. I like Tenet. That's a really good documentary, right?
Sorry, Gingerville, you can continue.
You can't just drop the entanglement word without us sounding like idiots. Again,
You got him.
professional.
No, but the word
idiots.
entanglement, it just means that these two states are intrinsically linked and they're not separable, is a better way of putting it, right?
No,
So if you
it's
have
not.
2
I don't know what that actually means, but okay, there's just 2 things together, and
this is the weird bit about quantum mechanics, is the entanglement bit, right? Superposition bit is not actually the weird bit.
yeah.
That even happens in classical, if you want to be like classical waves, right? They can be superposition.
Right, if we
Nothing
drop the 2
fancy there.
things in the lake,
The
it makes
entangle bit
sense.
is literally, they just are like joined together. You cannot separate them. There's no math model operation that can separate those 2 states. They're just now intrinsically
So
linked.
what scientists have joined, let no man separate, is what you're trying to say? Is that the rule?
Yes.
Okay. Bang.
There's a caveat there. I'm trying to dumb this down
Oh,
as much as I
dang
can. But it doesn't matter. Right. There's a reason. Right. So we've got this entanglement, right? You can entangle anything like really together. But in their sense, they have these qubits, whatever these qubits are represented by, right? And then when they get entangled, so you got 2 of them entangled. Now, of this state, before if you had 2 bits, you'd have like the 0, 0, 1, 0, 0, 1, and 1, 1 state, right? Mm-hmm. Now, together with those qubits, you're actually representing all 4 of those states at once with certain probabilities. So there's like, let's say, 20% chance it's in state A, 10% chance it's state B, 30% chance it's in state C, and 40% chance it's in state D. I had to add that up in my head. Yeah. They're kind of the probabilities it could be in that particular state, right? So now you've got all of them up computing, like all stored at once. Now, when you add more and more qubits and things, you get more and more of these different states that are all being represented at once. Mm-hmm. So I think like the latest computer, like common computers, like it's over 600 qubits or something. It's probably more than that now. I don't know. It's a big number in the quantum computing
Because it's
world.
2 to whatever that number is how many states
That's
there
like
are,
more
right?
atoms
Yes,
in
it's
the
2 to that,
universe.
yeah.
Why would you need a... So just help me understand even like a stupid question. Why would I need something bigger than like 64 qubits or maybe 128 qubits, considering it literally represents the probability of all values at
Because
any
that's
given
the
moment?
only bits they've got. Like in your computer right now, you've probably got like 64 gigabytes of RAM, right?
That's a lot of bits.
That's a lot of bits.
That's
That's
a lot
all
of
they
bits.
have memory-wise. That's all the bits.
Yeah, but the... Okay.
Yeah.
But we only
So yes, they
operate
can
on,
store
like,
a lot of
CPU
states. And in fact, they
theoretically
can not
only
just store 2 to the n. They do 2 to the 2 to the n. So it's really big. So 300 qubits is effectively equivalent to be, what, more than atoms in the universe.
Yeah.
Right.
If I remember
Okay,
correctly.
so but like CPUs process like a set like one operation at a time, whereas where these things are like, I don't know, seancing.
Well, they're still doing one operation at a time, but the thing is, because of their probability distribution thing going on here, right? It's kind of like it's doing it all probabilistically distributed across all the possible states. So it can do multiple, quote unquote, multiple things at once. Now, for most problems, this is where like most people may not understand. Quantum computing has got some only certain cases where it's useful. Most of the time, classical, as we know at the moment, is better for virtually everything else. Certain things are better with the quantum algorithms. So the most common one that most probably have heard of is Shor's algorithm. This is the one where you can decompose an integer into its prime components, right? Where
what do I have to do with
this can be done
integer?
in polynomial time. Sorry.
Prime components, Ginger Bill. Keep up.
The prime
come on,
components.
keep up,
The
shit.
prime again.
Yeah.
All right, sorry, keep
Yeah,
going.
sorry. I'm trying to think as well. Jokes are really hard to do when you're trying to actually think.
You're dealing with some professionals right now, okay?
I'm not listening. I'm just trying to come up with jokes.
Right?
I had a joke about web browsers and we went right past it.
All right, hold on, TJ, lay your web.
Can I
browser
say it
joke
now?
down.
Since we're paused, I was going to say Ginger Bill said classical computers are better at web browsers, so I was wondering if that's kind of like Ginger Bill currently co-signing on the state of the web.
Let's see how I'm putting the rubber stamp on it. Great. Yeah, there we go.
Looks good to me.
Looks good. Looks fine to me. Yeah, you got PR. Yeah, I'll just merge it. It doesn't matter. It doesn't matter if they pass the tests. We'll fix it later. Never do. No, but yeah, so that's kind of the thing. So then there's the last component when it comes to quantum computing, if I can think of, which is effectively interference and decoherence, which I'm going to merge together just to keep it simple, which is not correct, but whatever. Interference, you have to understand, is that these quantum systems, if you've ever seen a quantum computer, they have to be really, really cold. Like they're literally like fractions of a degree above absolute zero most of the time. And the reason why you want to get them cold is you don't want any background noise interfering with it. Because if you have background noise, it will make it noisy. And again, when these systems, they're not discrete like your computer. They're probabilistic, effectively. And if you add more noise to it, your result gets more noisy and noisier until you've got absolute noise at the end of the day. It's useless. So sometimes you'll have interference from these different probabilities. Like sometimes the probabilities will amplify each other or cancel each other out as well. If there's even no background noise, that's another form of interference, which can be useful for certain algorithms. Like, again, if you have two waves on an ocean or a thing, if they're in sync, they'll get amplitude. If they're out of phase, they'll cancel each other out. And then the last one is decoherence, which is...
Trash talking.
Yeah.
No, decoherence is the other one where you would... I'd say it's collapsing a quantum state into a classical state, right? Which is where you want to read it. You want to be able to read something in a classical state. Is it in this state or another?
Can you explain it in terms of monads? Because this feels a little confusing. Is this like a lift off?
Dumb it down to
monads.
monads.
Oh god, whatever the joke is, the endofunctors. I can't remember the flipping joke.
Look, Prime, they could be anywhere in the burrito until you open it up and look inside, and then they're only in one spot in the burrito. And how many times you close the burrito
Pretty
and look
much.
inside again, they're in the same spot.
That's
Actually right.
I understand it.
Okay.
Right?
Yeah.
Yeah. See,
Kind
monads.
of.
I wish
Yeah,
it
it
just
goes
used
like, yeah,
actual
sure,
monads.
whatever, man.
Well, yeah,
funny thing
monads
is, I
aren't
find
really
this easier than
burritos
monads.
either, Ginger Bill, okay? They're a computer construct, all right? They're not actually a burrito, all
I know
right?
there's not burritos in my machine, Ginger Bill.
There's not really burritos in there, dude.
Who's the professional idiot now, Ginger
Is
Bill?
this why you like
how
procedural
else do you cook your
programming?
burrito other than on a GPU when it's red hot? Come on.
You could maybe cook one on there. Okay, I'll give you that
Yeah.
one. I'll give you that.
See? And it's a good place to keep them warm. It's a nice little hot, warm room.
There we
I don't see
go.
the problem.
All right.
I have a quick question. I'm probably going to sidetrack this. Like,
That's great.
from everything
We're
you're-
not sidetracked right now, so I'm very upset that you're doing this.
from everything you've explained, it just sounds like it's so fragile.
Yes. Oh, it is.
Are they like burying these things like underground so there's just like no noise? Like,
No, so when you do, so to be very careful here, people who don't know, my specialty was not quantum computing. When I used to do it, it was quantum optics, which is still heavily related to this, by the way. So luckily, I can blag it enough, so I'm okay. So what they do is they don't necessarily put it underground. So when you make things very cold in that sense, what you're doing is, depending on which system you're in, if you're trapping, let's say an atom, let's just say you're trapping an atom, what you're doing is, temperature at the end of the day is you're reducing the jiggliness of something, right? Temperature is jiggliness. Technical term.
No jiggle.
So the way to imagine when you're cooling down an atom, right? Imagine it's an elephant and you're shooting ping pong balls at it. Right? If you shoot ping pong balls from every single direction, eventually you'll slow down that elephant. Yeah? Mm-hmm. Now, in this analogy, the atom is the elephant and the ping pong balls are light. Literally photons, particles of light. Yeah? So the way you do this, to get it to work, how do I explain it? This is going to be fun, explaining, actually cooling down atoms. This will be fun, right? I hope.
Ice? You use ice?
I'm having a lot of fun watching Crash compute this in a classic computer.
Right.
Jiggliness,
right? That's what temperature is. It's jiggliness. And what you're doing is you're trying to get rid of the jiggliness.
Because when things are cold, they slow down.
Yeah, that's what temperature is. It literally is less. If you've got more jiggliness, it's hotter. If it's less jiggliness, it's colder.
Yep.
You can't ever go still. That would be absolute zero. You can't hit that. Right?
Why not?
Yeah, why not?
That comes into quantum mechanics, and that's all to do with Heisenberg uncertainty.
Okay, well, you just checkmated me.
The
with
guy from Breaking Bad? Where does that come into this, Ginger Bill?
Yeah, say my name. Wait, no, so that's, to explain that, this is like, oh, great. Explaining quantum mechanics to people is fun.
So many new words.
So what that means by the quantum Heisenberg uncertainty principle is that when you measure something, there's like a fundamental something called action to the universe, and you can't go below it. So when you're measuring like the position of something, right? If you get below this limit, the product that you measure to get this action is the momentum, right? That then the uncertainty that you're measuring the position in, the uncertainty of the momentum would have to skyrocket. So actually that means it's now jiggling even more. Or if you got that down, you don't know where the heck this atom is anymore. Right?
Because we can't observe it. We can't send light or anything else at it.
The uncertainty of it,
it's going to hit it.
Where you are observing it, you think like the uncertainty gets spread so far. You can actually observe this uncertainty principle in like the macro world. It's not like a small level thing. You can actually see it in the big world. I haven't got a demonstrant already to do this. Just find something on YouTube. It probably exists already to find a little thing. But that's why you can't get down to real absolute zero, because effectively you're reaching those certain limits. So when you get this cold with this, and I'm just saying this
I will never explain to anybody.
Quick question, because I'm sure people watching this are going to want to know: can this thing explode and just like blow everybody up?
A quantum computer? You're saying?
I don't know, because if I had a quantum computer in my attic and then like things got hot, would it blow me up?
Great question.
It depends on the type of quantum computer, right? Because it depends on... If I remember correctly, there's different ways of making quantum computers. You can do like atoms, ion traps, there's photon-based ones, there's all this, right?
Yeah, you're right.
Depends on what they represent, right? Of course, I think I should clearly know this, right? You're in the know.
I don't know why.
Which brand of photon one do you like?
I knew that there's different types. Stupid me.
The short answer is yes, they could blow, because you've got lasers to deal with, and these are not like the big lasers. Also, this is clearly not what I'd wear in a laser lab, because a tie would be literally a health hazard. Because you going over a table and do that and like, damn it, I've now burnt my tie and killed myself.
That's how they find stuff out, though. Like, that's pretty much how microwaves got invented.
Yeah. I heard, the microwave. Someone is like, he noticed his chocolate bar melted in his back pocket, didn't they? Luckily, he didn't microwave his arse, but yeah, it's true. Just the chocolate.
It's true. That's real history.
Yeah.
You can
let's get back on track.
What's the radiation that develops in a lot of people's basements that they have to get tests on?
Microplastics.
No, it's radon.
Radon.
Oh, radon gas. Yeah, radon's literally an element, right? It's,
some dude walked through some sort of checkpoint, and he was just like so nuclear that it like was setting off all sorts of alarms. And they're just like, It turns out he was probably going to die pretty soon, but it just turns out they discovered that there's this thing that happens in people's basements. Like, real story. Accidents.
Well, it's not just basements, because
save
it usually happens where near coal mines. If you've got a lot of coal deposits, you have to worry about radon gas. Like, I live near my dad and my uncle and my grandparents were all coal miners, right? So they always had to be careful of that as well.
Did they have the black lung?
No, none of them are fine. They were all fine for that.
Okay, that's good.
Yeah. There you go.
All right, sorry. Let's.
But again, distracted. This is the whole point.
Quantum.
This is the stand-up.
Yeah.
We never go on topic.
Quantum
Yeah, this is
stuff.
good.
This is good. I'm actually loving this because I'm actually learning
Right.
something also.
So
I've got
the
a-
other thing,
I've
if
got
I'm
a
doing the
separate
atoms,
question.
There's a minor thing I've missed out.
go
Is
ahead.
also you have
You
to do
go.
it in a massive magnetic field, by the way, as well. You don't just shoot lasers at it in all directions. You have a magnetic field as well, which... The way I'm trying to figure out how to... It gets into...
Does magnetism just like help hold it because magnetism's so strong comparatively
No.
to like gravity and other stuff? Okay,
So
I'm
what
way
you're
off. Okay.
doing... No, this is a trick. What you're doing with the magnetism and a really strong magnetic field is when you... how do I put this? Only certain certain frequencies or wavelengths or colors of photons can get absorbed by atoms, right? By the electrons in the atoms. They have to be exact like certain frequencies. If you add an electric field, I'm trying to dumb this down, it can make those ranges a little bit fuzzier and easier to hit. It's about hyperfine
Aim assist.
levels and all
Got
this,
it.
right? Yeah.
Yeah.
It's aim assist, effectively. It's effectively aim assist. Because without it, you'd be screwed. Mm-hmm. Right?
Yeah, like me playing Call of Duty, I got it. I'm following.
That's why
super
if you win the
closely
controller,
right
you got the aim assist, it's fine. But the superior race clearly uses a mouse. So
Yes, right.
fine like that. But that's kind of what you're doing with the magnetic fields. But if I remember also correctly, some of the early qubit ones were also like MRI, like effectively MRI machines. Effectively is how they worked, which is a similar same thing. You have to have the massive magnets, but instead of like they would have been like photons, but not necessarily lasers. They would have done like radio waves, which is how an MRI machine works. Effectively, you got giant magnetic field, you shoot radio waves at it, and then the hydrogen atoms in the water will effectively re-emit those photons as bits of light again, so you can see it.
I haven't heard any of these words since I was in college.
Yep.
This is
Trash, you were
crazy.
supposed to be doing research for this episode.
Yeah, this is research, man. This is research. This will be on the
I
test
was
at
watching
the end.
videos
Sorry,
for
it's a
like
pop test,
5-year-olds.
pop
It
quiz.
was literally like this was like for a 10-year-old. Like this is beyond that.
All right,
Trash
let's-
watch.
Let's
Right,
stay,
but
let's
that's
stay on
it.
topic.
That's my crash
Okay.
course in quantum computing for you, done, guys. You should
Okay,
be
so
done
I've
now,
got
right?
I've got a question about them. So I get it. The thing that's very different about it is instead of ones and zeros, we have probability distributions. I feel like that's kind of like a big part of it. And then we can sample from those probability distributions like a lot of times. But it's
Yeah.
better if we can make the probability distributions be more probable to give the answers that we want.
Yeah.
Right? So that's where we have to write completely new algorithms. My understanding is
Yeah.
I have a SHA-256 algorithm. I write it for regular real computers that actually work and can go in consumers' places and aren't like a government conspiracy like birds. I can do those. I write it at my house. I write it down. If I wanted to solve SHA-256 for quantum computers, we have to write a completely new style of algorithm that is all based around quantum gates and stuff like this.
Yes.
So they have higher level programming languages. For maybe we should go there, and then I have questions
No,
about
no,
the
I
next
don't
thing.
think so yet. I think those
Okay.
different gates for people who are listening, maybe logic gates. You've got like and, or, not, those kind of things, right? They're logic gates in normal.
That's how
binary,
all of
classical
computers are
computers.
built, guys.
We don't
Every-
do
literally how they're all
gatekeeping
built.
on this podcast, okay? We're
Yeah.
not going to
Gate-
do any gatekeeping around here.
Right, no
we're
gatekeeping.
only
This is
OR
it.
gates.
Yeah,
OR
we're
gates
only OR
only.
I like Zors. Zors are nice.
Yeah.
Yeah, Zors are nice.
So, but
But on
maybe we
quantum
probably
computing,
should
you
say
have
though.
more gates. You have these
Yeah.
different things entirely.
Yes.
And they don't even have the same logic. So one of them is, this is like effectively it happens in like matrices, but they call it a Hadamard or Hadamard, if I'm not going to do the French pronunciation. So the Hadamard
Thank you.
ones, right? Because screw French pronunciations. I'll even get them wrong anyway, because that's not the correct pronunciation in my accent. And I'm like, oh, good God.
We don't
Right,
even like you.
Hadamard.
You don't. You're not. You weren't born in France, so it's fine.
Yeah,
It's like,
I'm
what
not
can I
very
do?
French. I'm English,
trying
right?
my best.
They hate me anyway, so it's fine. Just by, yeah. So we got the Hadamard thing. So Hadamard is normal Hadamard product in matrices is you just multiply each element by itself, and that's it. So it's like a dot product effectively, but for matrices. But the Hadamard product for quantum mechanics, not quantum computing, is effectively you're using this to change the basis vectors, the basis of the thing you're dealing with. So it effectively
basis
mixes
vectors are like X, Y, and Z. They point in a
and then you're
direction.
mixing
Thank you
them
for
up
calling
a
it
little
out, 'cause
bit.
my brain's
so it's like
melting.
instead of like having it this way, you're changing your basis to look like this or something. You're just
Okay.
rotating it around
There we
somewhere,
go.
effectively. And that's what the Hadamard product does, right?
And then
But
you can
that's-
use that to make probability distributions look different, right? That's my understanding.
Yes, you can do. Again, it's a simple game of the things to add together. And most of these different gates are just different types of matrices at the end of the day. And they do different things. So that Hadamard, again, I'm doing it wrong, is effectively just does a slight rotation kind of thing.
There's currently 3 whiteboards on TJ's camera right now.
Trash, can you see
Yep,
this? Trash,
Yes.
can you see this?
Yep.
Okay? This is like X and Y, right? But
Uh-huh,
really,
got
you
that.
don't want to do that. You want to say that this one is like 1 or something like this, and this
That'll
one's
do,
2.
that'll do.
Oh, right?
Get those cats out there, man.
I got
Nice
some. I got
cats.
my cats. I did my research. I'm coming
No,
in
you just
hot
need the bra
right
as
now.
well. By the way, they
Okay.
are literally called bras and cats because Dirac
Nice.
was an autistic guy who thought it was funny.
No!
Bras and
I drew on
that's,
my
that's
shirt.
actually gonna stay. That's 100% gonna stay, and it's ruined now. Sorry.
It's.
Oh, well.
I'm gonna have to call Michelle and get a new one. Okay. So you start, and you've got this guy. This represents a state vector for a
Yep.
for a qubit, maybe.
Yes. That's
nice.
it. Yeah, yeah. This is good. This is good.
Okay, got it.
Love it.
Oh,
I'm trying to see where his knowledge ends because he's doing
We're
good so far.
cooking. Chat. Okay, chat. If you're out here, comment Pog. Teach whiteboarding. Pog. Thank you. Okay. So then we can do a Hadamard thing. We can reflect it across an axis. Then it looks like this. maybe?
I can't remember exactly the matrix, but it does
It
effectively.
could do
like-
something like that.
does
so we
something
can
like
move
that.
it
Yeah,
around.
whatever. We'll
But
say
Far
just
less
that.
confidence in that next line you.
Okay. You're so right. I'm gonna
You're like,
erase that. You're so right. Thank you.
You're absolutely correct.
No! It's worse.
Now
I
you're
swear
thinking- you're
TJ's
thinking about
reading
it too
right
much
off the
now.
screen. I think he's
That's close enough.
ChatGPTing
That'll
right
do.
now.
That'll do.
But then what we can do, this one's not necessarily that helpful for finding out a better answer. We can also rotate them. I don't remember how we do that, but there's rotating gates that you can put stuff through. So imagine, Trash, you can get this arrow closer to this one. Eventually you could make it point at only ket 2. So then the chances of getting the right answer are higher and higher and higher. And then we've solved the problem and I can hack your password. I don't know if that's right. How close am I, Ginger Bill?
I mean, not the password hacking bit, but like you could do. Literally, it's just linear algebra, man. It's just linear algebra.
It's just linear
Loads
algebra.
of matrices.
Yeah, but so are AI, just linear algebra. Okay, so
Yeah,
I have-
everything's linear algebra at the end of the day, man.
Okay, can I
Everything's
ask
either linear
another
algebra
question?
or wiggles.
So this is how you guys are describing it, and it just makes it really confusing. Or at least this is how all quantum computers. Here's my whiteboard. Okay,
Yeah.
now it's my time.
Go ahead. Yeah.
All right,
That's a
this is how
blackboard.
everyone describes everything quantum, and I'm very confused by it. Is that you first start off with a state, and you somehow feed it a problem, right? You
Yep.
feed the quantum all the little gates these little problems, and somehow it's able to take that problem, and then when you look at it, the probabilities are just aligned in the giant cloud space that is 2 to the n or whatever it is. Possibilities in here. It's just the correct n. It's the correct 2 to the n or 2 to the 2 to the n space, and it's just like, here's your answer. It's these 105 bits, and you're just like, how does it go to the correct answer? I don't understand that leap where it goes from probabilistically all the answers, but there's one once you observe it, and it's the correct one.
Let me try, Ginger Bill, and then you can tell me where I'm wrong.
Go ahead. Go ahead.
Okay.
All right, so it all starts with the flux capacitor.
All right,
Okay,
Ginger, go ahead,
okay.
start explaining it.
I'm kidding. Let me try and answer it for real.
I'm with you.
Okay, so the box that they put it in, for me, this is the thing that I think I'm getting, but I don't know for sure. It has a custom algorithm to solve the question that you are trying to ask, right? They have to build, just like an FPGA, field programmable gate array. That's literally, we build a custom computer to solve the problem that you want to put in. I built an FPGA that could play the game of life, where you would press buttons and it would move you on stuff, and then you would press another button, you would go, or no, not game of life, shoots and ladders. Sorry, I got confused because I know Prime loves game of life.
I do.
They could play shoots and ladders, and it would be like you landed on 13, boom, you jumped all the way to 27. Cool, right? And it was just an FPGA. It could only do that one thing. We will build quantum computers for now because we don't have a programming language for quantum computer that can solve particular problems. Maybe this Willow chip from Google can be reprogrammed to do other things, or it has lots of gates or something that can let it do that. But like, so you have to build a custom quantum algorithm that can do basically a matrix transformation that takes some input and puts it into the output that you want. The thing that's different about it is it can do not like a lot of them at once, but it can do, I don't know how to describe it. So I don't know. There's my closest thing.
It's not that it's all at once. It's just that is the kind of mathematics you can do.
Yes, thank you.
Right? It's just different is the better way of describing it. Yeah, it's hard to explain because it's like
that answered it. Okay.
I'm more confused than ever right now.
No, but the black box is not like, I feel like when people say quantum computing, they're like, as soon as we get the quantum computer, passwords are dead. And you're like, we don't have a SHA-256 reverser quantum computer algorithm yet, right? So we would have to still find a way to express that transformation in quantum computing gates or some higher level construct that could do that then could do the math to solve that question for you. And generally speaking, my understanding, maybe I'm wrong on this one, Ginger Bill, it's not that it solves it instantly, but that then it's not like it's O of one time when we figure it out. No. Now it's that there's some, instead of being like SHA-256 and it's going to take 1 trillion years to solve it, it's like now you could do it in like a day.
To use the canonical example of a quantum algorithm, which is Shor's algorithm, right, which is the one where you find the prime factors of an integer. On a quantum computer, you can factor like an integer n, right? And Shor's algorithm can do this in polynomial time. In fact, I think it's proportional to the log of n, the time it takes. Whilst on a non-quantum computer, effectively, I think it's like much slower than log n. I don't think it's exponential, but it's like maybe n factorial, or it could be something like that, which is effectively exponential. So it's very, very slow.
Factorial was bigger than exponential.
It is, but it's close enough on the same order.
Okay.
I'm being lazy with my terms here. But in general, that means it's very, very slow. But the quantum one, they can do it again log n, which means it's actually a lot faster for this particular algorithm. Is how it does it. And there is a way of doing it, but it has to be through the quantum algorithm. And the way you're doing it is you're effectively doing through this estimation thing. And a lot of them are, when you're saying asking like the algorithm stuff, I'm trying to remember Shor's algorithm off the top of my head, which is hard. And I'm also looking here, just even then, it's still not helpful with Wikipedia notes because Wikipedia is written for PhDs. Yeah, but effectively a lot of it is just
code on. You can read it.
Yeah, this is a lab coat. This is actually my old lab coat, but made into a Halloween costume. So yeah, this is Halloween. There you go.
Your career is now a joke.
Yeah, it's a joke. But it's not my career anymore. Unfortunately, I don't know. I've had a lot of thought in it. Okay. But yeah, it's kind of one of those things where you just do a lot of the math and you can break it down into these quantum logic gates and such this way, but it just figured out what that algorithm is. So the question is, how does it do this in the log n time? Well, it is kind of doing more of these estimations at once, which is why those probabilities work. And the ones that don't work effectively, they get filtered out. Another way of thinking about this through is if I can you know when you do audio and you've got an EQ, right?
Yep.
We do different bandpass filters, aren't you?
Yeah, good point.
You're effectively doing that. That's
Nice.
how you filter out the stuff you want. So if certain things come in and they're well off the spectrum, they get filtered out. It's like, oh, they're not probably the right answer, nowhere near. They'll be much lower down. Where the ones that might be closest to the right answer, they'll get more amplified up, right? This is like a Fourier transform thingy, a quantum Fourier transform specifically, but it's that kind of thingy, my bob. It's really hard to explain because I'm not going into real complicated mathematics. I don't want to do that.
Thank you for not doing that. Thank you for not doing
I would have liked that.
I'm
we'll do that on
people
separate episodes.
Watching this video in the comments, I'm trying. guys. I'm trying.
The
And people
thing
say,
is,
that's
no
not a good
matter
way to
what
explain
you
it.
say, though, about quantum mechanics, quantum computers, somebody
Yeah.
in the comment is going to say, well, they've already solved it. They've been lying to us all along. So somebody's going to be mad in the comments no matter what.
Yeah,
Gingerbill.
true.
You don't have to be worried.
Can't keep them all happy, no matter how well you explain things.
We need to go dumber right now.
I don't know. I actually don't know if we can.
That's all I'm saying.
Follow-up question for
Yep,
this,
yep.
Gingerbill, for Shores. It's not that we put in a number at the front into our mystical quantum computer black
Yep.
box, and then in one shot, we're guaranteed to get out the prime factors, right?
That's right, yeah.
Okay, so then it runs multiple times with a new
Yep.
state vector, just like
Yep.
if we wrote a really dumb classical computer example of like I'm gonna find the prime factors by just like literally like guessing random numbers, and I'm gonna go start at 0,
Yeah.
and I'm gonna go to obviously not 0. I'm gonna start at 1. I'm gonna go all the way to here and see which one's factor. I'm gonna start, and then we like just keep guessing until we find them because it's a search problem,
Yeah.
right?
And so there's just better search, or there's a better way to branch prune, is what you're saying, is that you can...
Yes. Because when you think it's about statistical, right? Because again, with the quantum stuff, there's a lot of noise due to the stuff. Earlier, classical computers had a lot of noise to them as well, by the way. It's just that nowadays we've gotten so good at this. In fact, well, not really. But we've gotten better at it nowadays that you don't get the noise. Sometimes you hit it, like especially like the newer RAM stuff where they're so crammed together, like the transistors are, where they start to get like you get error happening with the, like the RAM, like even in classical, because quantum effects start happening, right? They effectively things get noisy. The electrons jump between everything, and I say electrons, but I mean everything gets fuzzy. So you get that's why you need like error correcting memory a lot of the time sometimes to get rid of that. But when in quantum, it's fundamentally, everything's just noisy, and if you do multiple times, those multiple runs will then clean things up. So think of it as effectively as like like path tracing or something like that.
And then our as we do more iterations, our state vectors probability ends up looking more like instead of being like, we have a 0.3, 0.4, 0.2, that's 0.1.
Yeah, that's enough. Yep.
We like end at something like, oh, we're pretty sure this one is 9, or I guess it would be like 5, 0.0, 0.0, and then like 0.45. Like if we had two slots that we needed to go to, be like, oh, well, that's actually these don't go to 0 though. They'd be like 1 or something like that.
Yeah,
right?
very small. Yeah.
Because we can make them 0, that would be not right. But we can make them really small, and then we're like, oh, when we get out
Is
the
that
thing
absolute
at the
0?
absolute 0, can't do it. Absolutely not.
Actually,
More like.
okay, so
because the
I
hobble
want
bloody
to go on a
bloody
little
bloody
tangent,
thing.
right?
Okay,
Yeah.
I'm going to minor actual like
It's your
nerdy
turn.
tangent.
Yep.
Uncertainty is actually intrinsic to the world. It's not like the quantum thing. It literally is what is the level of your measuring tool. If you've got like a ruler or a tape measure or
Significant
something,
figures.
yeah, you've always got like literally like if your ruler goes to I don't know in say millimeters, the error on that's going to be like half a millimeter, right? When you can't be any more accurate than like
what
half
are
a millimeter.
millimeters?
Okay, let's
Can you
do
explain this
30
in
seconds
terms
of
of
an inch,
America?
right?
Oh, thank
so in
you,
30 seconds of an
finally.
inch, yeah.
Finally.
If you have 30 seconds of an inch or 16th of an inch, we'll say 16th of an inch on your tape measure, right? Because they usually go down to 16th
Yeah,
of
then
an inch,
obviously
right?
you have a 30-second error potential.
But you got a
right there,
30-second error, right, on
Yeah,
any of your
naturally.
measurements. So fundamentally, your error is on your measuring stick. You can't get rid of this uncertainty. Your uncertainty is fundamentally there. This is not like a quantum thing. This is just a measuring stick thing. And you could hypothetically get less and less and less to make it more accurate, but you get more accurate in the thing that you're measuring. The thing that quantum mechanics brings in is that actually there's something associated with it. You would start losing that information as well. Like you can get more accurate on one thing, but once you get very, very close to this like fundamental limit, the thing gets fuzzier. Right, the other thing goes, the other uncertainty of the other thing, and this, if it's position, momentum goes. If it's time, energy goes. Right. So they're the kind of the different things, your uncertainties. So that's another thing I want to very get clear. The uncertainty principle is everywhere. You do it in real life. Like it's not just
I got
quantum,
a good example from real life. Trash, I know you'll relate to this one. If your kids are playing in a different room, they act different than if you're in the same room with them. Under observation, the children act differently. That's the same thing with electrons.
Okay.
I don't know if that's actually a good
So
example.
if I go look
Just-
at an electron, it's gonna slow down.
it's gonna play really nice. It's
Slow
gonna
down over
play
there.
nice with its brother and sister.
So I just right now, probably looking at like a bunch of electrons. They're acting differently now.
Yes, they're acting like they didn't
Let's go
do
with
anything. They'll have that weird casual stance where they're just like this. They're like,
Me?
oh, hey, Dad. We're just hanging out. It's totally normal in here.
I'm just gonna start walking around my house. Hey, I see you. See you over there.
Okay, I've got a follow-up question about the next part of quantum computers I don't understand,
Okay.
Ginger Bill. What are people planning on actually using them for besides spending a lot of research money?
That's a
Cryptography,
very
right?
good question.
Thank you.
And the answer is, I think it's just spending a lot of research money currently.
Yep.
But a lot of it is like, again, they want to break encryption. A lot, like, again, Shor's algorithm is a good example of this. If they can break
Right.
a lot of basic, like, RSA encryption, you've broken it.
You can have all
Now,
the
I know there is some
Bitcoins.
encryption which is, like, quantum, like, safe already. But,
Elliptical hash
yeah. I
or
think
elliptical
that's-
curve. Sorry.
Whatever they are, elliptical curve madness. Some of them stuff is, like, it's impossible to break with quantum computers. They just don't have an advantage anymore. So a lot of
It's
this
'cause
is they're
it's
just trying,
iterative, right? It's because it's like you need step-by-step process, and the resolution of each step
Yeah.
is now.
Oh, that's really smart.
I don't know if that's true, but I think it's something along those lines where there's like a dependency problem that becomes really difficult for it.
Yeah, and I know there's certain other algorithms, because again, it's all probabilistic. Some of the algorithms also do, like, you know, like a random walk. Have you ever heard of a random walk before?
Monte
I go on
Carlo.
those.
Boom.
Like Monte Carlo, yeah, but a random walk, for people who don't know, imagine a drunk man in a field. He will walk randomly eventually, but eventually he will get out of the field after a
Debatable.
certain amount of time.
Give him enough time, trash.
Put me in a field right now. I'll
Right.
see if I can.
Wait, right now?
I'm going to
That's in
sleep.
2 dimensions, by the way. That's in 2 dimensions. And then when you get to 3, it's fine. And but the thing is, there's also these called quantum walks, right? Which is slightly... It's not a random man in the field at this point. It's a very quantum, tiny little thing. Not really, but it's just like, it does quantum stuff, right? And there's a lot of algorithms that help when you do, like, quantum walk things, right? So that's another one to use with quantum things. And they can make it go much, much faster with quantum algorithms than they can do with classical. I'm just trying to think of anything else which I can describe.
Well, here, maybe to help jog your memory, I did draw this picture of Trash. He is very confused right now. And so I just want to let you know he's still...
Doing.
That might be the thumbnail.
Oh,
That might be the thumbnail.
I tried to give you anime eyes. I'm not very good at drawing, so I
those
couldn't quite
look
do
terrifying.
it. Thank you.
Right into my soul.
All right. So I want to talk about the Willow thing, because obviously the
Yes.
example that they gave was that they're going to help do predicting of various structures of some sort. I think it's not protein structures. It was like structures for specific organic compounds, if I remember correctly. I can't remember exactly what was their examples. But does that mean, based on everything you've just said, that the Willow chip really truly is like a single serve chip, that it can only do this predictive thing? Or are they reprogrammable like field programmable gate arrays?
I don't know fully, but I think they're probably single-purpose chips currently. is
Wow.
my
Okay,
guess.
and these chips you have to also run at like negative 271
Yeah, like very, very cold.
Celsius.
And what is it, negative 486 Fahrenheit, or whatever it is like that.
No,
Something
we
like
don't.
that.
We don't use those units. Okay, Celsius is
Oh,
pretty good.
okay.
We can use Calvin, though.
Yeah, it's at like
Big
1
fan
Kelvin.
of the close, yeah.
Yeah.
Much less than 1, actually, but yeah.
Yeah, idiots.
Yeah,
I was gonna call that out, but I didn't want to.
yeah. Very, very cold is what I'm saying, yeah? Because they
Just
want to
saying,
minimize
Trash.
the noise. They want to minimize the noise. They have to get it very cold. They want no noise in the thing, like that. It's
Okay.
just...
So when you say they have to research, that means every single problem that potentially contains quantum supremacy, they have to first like hand construct, not just like, these are not FPGAs where they're more general purpose. They actually have to do like ASICs for every single problem, except in the
I
quantum
think so.
realm,
Again,
which
someone
is
in the
much more
comments will tell me I'm
confusing.
completely wrong, and they're probably right in being completely wrong, because again, this is not my field. I know I've got the lab coat, but doesn't mean it's
thing
actually
off.
my field.
He's a compiler dev these days. Okay,
I am
do you know
compiler, yeah.
any reason why like generalized programming languages can't or currently don't exist for this? Like, how is there not just some? I assume because all the
I
problems.
think
in
there
some sense
probably
the-
are, but
Okay.
they're probably the equivalent of assembly at the moment. We haven't had that revolution to get to like the equivalent of like C or Pascal for computers yet. We have all the Algo
Or Odin,
Fortran, right?
even.
Yeah,
Odin,
like
yeah.
not because the thing is, modern like normal programmers things, they're all classical. They're based on classical logic, right? Get ands, nots, ors, zors, that kind of thing. But when
So
you've got
they
all
do
these
have some stuff, though.
yeah, they probably have some stuff already, which is why
Yeah.
they represent all the gates. But it's effectively like drawing circuit diagrams at the end of the day, is what they're doing.
No, they have an open source Python circuit, but it is
Yeah.
basically like what you're saying, though.
Yeah,
in
it's,
the end,
as I said, it's effectively assembly language level,
Right.
not...
you construct the circuit. It looks like
Yeah,
with
you're constructing the circuit
actual
with
thing.
Python. It's not like Python is being ran on these machines.
Yes, right. Yeah,
You're
yeah,
using
yeah,
Python to construct the thing. So it's kind of like... Effectively, you're just writing a compiler.
Yes.
And that's why. So I think the reason why they haven't found this yet, because also it's like they don't need it. Like think back in the day when it was von Neumann. Not a joke. Von Neumann believed assembly language was not programming. So only a real like person should literally write the machine code. Like he believed, like, oh yeah, you should. If you're not doing real programming unless you're doing machine code.
I do love that von Neumann was like effectively just like a Twitter rage baiter back in the day. Just like, yeah, that's not real programmers. That's not
I
real
would-
programmers.
Dude,
Yeah,
I
he
would
I think
have
he told us
loved
one of
seeing
his,
him
like,
on X.
say students, but like one of his postgrads saying, you know, you shouldn't be making. Why are you making assembly? Just write the machine code. Come on.
I also did, by the way, just look up Willow. According to some searching, less than 20 millikelvins is where it needs to run at.
Pretty
So
cool.
that's very cold.
Yeah.
So is there
cool.
is there a future where people can actually run quantum computers, or is this forever in Sergey Brin's basement? Like you just can't. You have to
So
be
this
the
is-
ultra wealthy company to be able to have any access to this in the next 50 years.
So the answer is most likely most people's basements for the next few decades, unless if they get like let's say photonic based ones better, because usually they can work at multiple temperatures or whatever, or if they found now a room temperature semiconductor.
X was really hopping with that. When was that last
Superconductor,
year?
right? Not semiconductor, superconductor, right?
Sorry, superconductor. Sorry, yeah, superconductor. Sorry,
Okay,
I got my
yeah.
words.
I
Again,
was
with
about
an
to say,
S.
dude,
It's
my
close enough, yeah.
semiconductors are going hard right now at room temperature. I don't
Yeah,
know
yeah,
what you're
sorry.
talking about.
Right, so very superconductor. So why am I saying this? Get it right. Superconductor, right? And because at the moment, most of them, there are some superconductor-based quantum computers out there. But again, you have to have them very, very cold.
Interesting.
If you
Okay,
get them
so
room
that's why
temperature-
people were so stoked about that. I thought it was just like about making trains go super fast. I
Oh,
had
no.
idea that
Like,
it had
yeah,
anything
but the
to do
thing
with
is
quantum.
about, if you have
Those are-
superconductors, you've got zero resistance, zero impedance. So you
Yeah,
could
that's why I
literally
thought it was
have
about trains
no
and
energy loss.
railguns.
Yeah, you could have everything. It's
The
amazing. You'd have-
conductor, they already have conductors on trains, bro. And they're super in my book. Okay?
Yeah, it'd be amazing. Like the amount of energy loss you get from a power station is insane. But I'm not doing this joke. I'm not playing along, Teach.
Mr. Bill, you made the same face Trash Dev made when he's been listening to you. Also, you're just like, huh? Like, I just watched it just divide by zero for a second. All right, Teach, that was pretty good. That was pretty
Thank
good.
you.
Okay.
Yeah,
Thank
good.
you.
That was
I
good.
literally thought that's the
No.
joke you were making. I thought you were saying the trains thing for doing the conductor joke.
No. I was just being serious because I thought it was just about like being able to transfer things super fast and super easily.
I thought you were setting me up for it. Like, yo, all right, I'm bumping over here. Like, be ready to spike this.
Well, that was
Okay,
beautiful.
so is it really just like... Okay, I'll just put my cards on the table. It seems to me like a crazy conspiracy to try and break the internet and be able to get backdoors into everything. That's why people are super interested in it. Like, I don't
That's not
get-
the main one, but there's loads of other things. Like the other one they were talking about is like molecules and such, right? So this isn't the exact paper that they're talking about in there. The actual paper that Google published at the moment, which is, and I'm going to say the title because it sounds fancy anyway, Observation of Constructive Interference at the Edge of Quantum Ergodicity.
They did use the term ergodic in there, and I had to look up what ergodic meant, and then when I looked it up, I had no idea what it meant. It's like one of the
it's a
first
fancy
words I've
word.
ever read the definition, and I was like, can't figure that one out.
Yeah, I wouldn't worry too much.
Here, hold on. For those that don't know, let me just give you like just a quickie in this paper. Hold on, I have it up here. right here. This is the thing with ergodic. It goes like this: as entanglement growth with size as entanglement grows with system size or evolution time, the resulting dynamics are often ergodic. And I was just like, I don't know what that word means. I was trying to read the paper, and ergodic is relating to or denoting systems or processes with the property that, given such sufficient time, they include or impinge on all points in a given space and can be represented statistically by a reasonably large selection of points.
That was way too many words.
Again,
to say.
go back to the drunk man in a field. Eventually, he'll hit every single point in the field if he doesn't escape it. Right?
Yeah, real. Okay, yeah.
That's
okay,
another way of
I
explaining
can follow that one. I can follow that one.
Okay.
Yeah.
See?
See? Bring it down
Got it,
to the
got
drunk
it.
man in the
give
pub
a
level.
sufficient amount of
Ergodic.
time,
I'm gonna start saying that all the
wander upon
time.
the entire board. Okay, I see
Correct,
what you're
yes. Yeah, that's what it means, yeah?
Okay.
That's all it is. And when they say state, in this case, or a space, when they say space, they don't mean literal, like, a space in a field. They literally mean, like, oh, it could be like there's 3 bits. Like, could it be in all 3 bits, different states of that? That's all that means. It's like a very abstract conception of what a space is. The possible, like, probability space, or the
I love how you
state
keep
phase.
saying words, and it's just,
Yeah.
I think I'm, like, hard-coded on my clarity at this point.
Yeah, I'm so used to believing, all these words. There's too many words.
It makes sense.
Yeah.
Okay.
Again,
I
the
don't,
drunk
I
man
don't
in
like
the
how
field, I'll
Jesus
keep
like,
to
I don't
this
know
with all my
anything. And then he
analogies.
started saying a bunch of smart things. I was like, he knows what
Trash,
he's
I
talking about.
was watching videos too. Guys, I'm pretty much a quantum expert. I like everyone else on Twitter. I spent one day researching it, and I
you
know
need.
everything. now.
These are my notes. Superposition, entanglement can be both values at once. Has to be cold. Those are like fucking
Close enough. Close enough.
That's a lot.
That was my
Trash.
summary of
That's
everything
good.
I learned. And then we went far beyond that. I was like, yeah, I can't be in this conversation anymore.
Trash. Those are good notes. Honestly, every quantum computing article should start with those, because even just, hey, you're gonna have to, as far as we can tell, keep this at basically 0. You're like, oh, so not everyone's gonna have one in their basement. Like, it's already
Yep.
like you're just not gonna happen, at least for a while.
I'm going to start saying ergodic.
Yeah,
It is
that's
so
a big
good.
learning, Trash. Put
If
that
I
one in
can
too.
use it in
But that is just a
successfully,
fancy
I'll
word.
be so happy.
They're just stupid physicists using stupid words, is all I'm saying, okay?
They
By
do
the way,
like
I also
big
brought
words.
props today, because I actually have got some molecules
Oh!
to yeah. I have loads
What
of
are
these
those?
things.
Qubits? What you got there?
Yeah, right. Oh, no, I've just broken this one. Oh, no. Where do I put that back?
See, if that was...
Science.
Would we have
There we
blown
go.
up if
Right.
that was...
This one, I think some people might know this. This is just glucose. It's sugar. That's just sugar.
I had no idea that was
Delicious.
glucose.
Dude,
Right,
Trash, you should
beautiful.
know that one, bro.
And then this
I
one,
eat it. I
what
consume
am
it. I don't know what it
getting
looks
from
like.
this stream is adrenaline, right? I'm just making some props.
Nice.
Oh, nice.
So there you go. There's adrenaline. Imagine
Okay,
there's
so then
hydrogen on here as well.
explain why do quantum computers matter for seeing the shape of these?
So a lot of these things is that, not those particularly there, but we'll say it was something like proteins specifically, because a lot of like medicine is based around figuring out proteins and their shapes of them. Because they may know the chemical like representation, but they don't actually know how it's oriented. Now, I know there's a lot of people doing that with like manually doing this and such, but if you could get a quantum algorithm to actually just figure it out, that's much better, right?
That makes
Weirdly
sense.
enough, AI is doing a really good job at the moment of this.
Yeah.
Right,
I'd
that's one
assume
place
that. They're
AI has
good at
been
search
really good
space.
at. Yeah.
Yeah.
Because it's effectively, it's again, statistical, this ergodicity thing, figuring out all this. It's a searching algorithm, and quantum stuff is really good for searching for things. That's where the quantum space is all doing. It's like it's doing all the different searches around finite probability. So if you can find the right orientation and like mapping of a certain molecule, then it helps. Like, again, here's adrenaline. Look, there's a floppy tail here. And imagine this was a fancy thing. Like, sometimes it could be the orientation, like, oh, this is the lowest energy level in this orientation, rather than this one, which is very, like, high energy or something. So you're
For
trying to figure out
adrenaline,
the-
that makes sense.
Yeah. I'm kind of doing it, but I got props, okay?
Yeah.
This is just cool.
Okay,
I like
so
making-
let me just walk it back to make sure I'm understanding.
Hmm.
We've got molecules; they exist. We believe in molecules. I'm following
Yeah.
so far.
Yeah.
The shape they are actually makes a difference, because like we do stuff like inhibitors and receptors and all this other crazy stuff. They gotta
Yep.
like match up next to each other, like in physical, real space. Like it actually matters whether it's a curly Q or whether it's a straight line
Yes.
for the medicine to work. Otherwise, it like doesn't block the thing or it does block the thing.
Yep.
Okay, so then we're saying we got to figure out what they look like, because that actually matters for us to try it. And we got to try like a lot of different kinds. Maybe adding one more little guy here or doing one little guy over here or something else is going to change the shape a lot. What's the most likely shape that they're going to be so that they can do the medicine-y thing or whatever, right?
That's a good answer.
Okay. And so then we're saying we have this really big search problem that follows a bunch of probabilistic rules. That seems like a good example of where maybe we could find or narrow the search space. Like in the bouncing ball example, which we didn't get to show Casey today, but maybe we'll get a separate clip of showing Casey that and just put it into the episode right here. I don't know. They're like, this is 13,000 times faster for this random thing. So you're saying, okay, we could search for the shapes of the molecules, like in this example, 13,000 times faster than we would with old classical computers. So we could test like a lot more different kinds of drugs faster and more cheaply, and then we could make new medicine fast.
This is another whole point of quantum computers. Yeah, it's one of those where it's effectively most of these are searching algorithms. When you look at most of the quantum algorithms, they're all forms of searching algorithms.
Right.
Okay, so does that mean that the you know how there's like I donate my computer to medical science and it goes and it does a bunch of protein looking and all that?
Yeah.
Is that effectively because even if Willow was a thing, it only runs in Larry's basement. Therefore, the donating your computer to science is still producing in absolute terms many more, even though it's 13,000 times faster than a supercomputer. It's just like, well, we have 1 million people doing it, so it's like this one always wins because it's just so much easier.
Yeah, at the moment, but the whole point is if you get these bigger, more, faster and everything, because that 13,000 times one is they're talking about this specific algorithm, which I think
on their particular
not in the
hardware.
paper, but in like the articles I was reading, not the paper itself, they were calling it quantum echoes. What it means is they're like, it's how fast you can scramble this data, then unscramble it. That's effectively the algorithm they're talking about. It's like a scrambling, unscrambling. Like you've got eggs, you scramble it, then you figure out a way to unscramble the eggs. And then they're able to do it 13,000 times faster than the biggest supercomputer at the moment, apparently, which is impressive. But again, it's this very specific algorithm they've designed it for.
Yeah, and if you need to change the algorithm, you'd have to refab the chip and everything. So there is like limitations in time and change and unknowns in the problem. So every time you hit a roadblock, you're like, all right, back to the classicals because we got to do a year.
And I actually
R&D
wonder
to
what
make
the
it to the
failure
next
rate
one.
for those chips are. Like how many chips they have to be made to even make them work. Because I know, like in silicon,
they say
like a lot of chips
statistically
are
in the
bad.
U.S. entanglements don't, like 50% of entanglements end in separation. So I'm not sure how long these chips actually last for.
Yeah, me neither. I mean, too much
Did you
noise.
is that a real statement that you just said?
One
Did you just
person
make that up?
in that relationship
he made a
goes
divorce
cold and it's
joke,
done.
bro.
Okay.
Yeah.
As soon as he said it, I just got so confused. Like, my eyes just like widened on that. I was like, hold on. Did I miss something?
Why is it only in the U.S.? This is crazy.
Dude,
What
that's
do you mean
pretty
in the
much
US?
that's pretty much the plot of the Dark Forest trilogy.
I mean, it is kind of sad that all my quantum knowledge comes from the three-body problem.
Hey, that's a good book. It's a good book.
Yeah, but
Agreed.
is this also like a Christopher Nolan documentary,
Yeah,
or is it
crazy.
real?
It's also a
Wait,
documentary.
which one's weird? The book.
No, not
Yeah,
the
the book
show.
real
The show
happened.
is terrible. The show made
show
no sense.
was-
I learned no.
I've only
quantum
seen the show.
physics
Didn't
from
read the book.
No.
I like
Oh.
the show because I didn't read the book.
Trash, you have to say that, bro.
Dude, the show has to be even more confusing without the book. It's like super. Like I was watching, I'm like, what the hell is even happening here? Anyways, okay, we got to get back. We got to get back on topic here. We can't be talking about that show. I don't even know what the topic should be. At this point.
It's like I was like, so where are we going from this?
Okay, I've got. I'll do another one then. What are the odds that we have or maybe a better answer or a question would be, what is the timeline you expect? Because what I found very funny is Google is like, bro, this is the first time anyone's ever even done anything with a quantum computer.
Yep.
That's like what they said. I felt like
pretty
was
much.
like, this is the first time anything's ever been done. And it's way faster than a classical computer at solving this thing that only quantum computers would care about, which I was like, okay, sure, fair enough. So, like, let's say, I mean, they may throw $1 billion at something to make it help them find a particular drug. So, but that doesn't, in my mind, that doesn't really count. That's just like saying we spent a bunch more money on something to do what we could have done with regular computers. Like imagine how many AWS Lambdas you could rent for $1 billion, right, to run your thing. So like, where do you have any guess or any feeling of when like a commercial application, not a research project, but like a commercial application is like, oh, we rented out Google's Willow Chip for a week so we could run drug tests, and it was cheaper for us than the equivalent, classical computer. Is
But
there
could
like
you
a
even rent it out?
horizon?
Right? Because wouldn't that be the problem?
Just
Is
be
that every
IBM.
drug test would have to be like unique and bespoke and hand rolled?
They have some stuff to run, some amount of reprogrammability onto the chips, I think, but it's not like you can't write like a for loop. You're putting like the gates and connecting them, and they probably have some stuff. So I think it's not literally full refab every single time.
But I have no idea on the time frame. Is all I can say is
okay, cool.
That's my answer. I have no idea.
Yeah. Okay.
I was in an interesting talk in 2010, which was like the future of
was in
quantum
high school,
computing. And it was at MSU, and he was talking about by 2025, the government was saying that you should be like more quantum secure, and by 2028, you should not have any RSAs left. Was kind of the time frame, and so now we're kind of arriving to this time where it's looking like things are actually kind of falling into place. Where maybe in 3 to 5 years something could be, they could start hacking, maybe only like 1K RSA, even though we're at 4K. But that's only going to take an extra couple bits before we're at the next level. And so I was very curious if you believe in his hypothesis, which the guy standing there he made a really great hypothesis, which was if the government tells you by this time you should be secure, the government already has that technology and is just like way ahead of the curve. Do you think that the government actually has good quantum technology at this point? It's just not releasing Area 51 space lasers and shit, or is it just like, or is this all fake?
That's a good question, actually.
Yeah.
Sometimes the government has technology before the public does. A long time before.
Yeah.
But the question is do they have this? And sometimes the government also just has like random advice, which is like pulled out of nowhere. Like they sometimes do this, like just to sound like, oh, we'll make sure up to date. Like, make sure it's by 2028, guys. Kind of thing. Like, I don't know. It's like
they're still running COBOL. Make sure you're up to date, everybody, by 2028.
Yeah. But they might do. This is the thing. If they do, we aren't going to know. And if I did know, I wouldn't be able to say anyway, because I'd be probably under the Official Secrets Act. So, which I have already signed before for a previous job, but like, yeah.
Ginger Bill confirms government conspiracy, online.net right now.
Secrets are no fun.
Look, if I knew, I probably wouldn't be able to tell you. And if I didn't know, I still can't tell you.
point.
I gotta put my tinfoil hat on. We all need tinfoil hats.
You're helping us understand quantum computers right now.
Exactly. Look, here's how you measure it. Like, there might be
What's
an
that
actual
word?
state of me knowing. It's just your knowing of it is, you've only got a probabilistic underknowing of it. That's it. That's done.
Okay.
I got an ergodic keyboard right here.
That's my manager. Can I buy some ergodic office furniture?
Trash then, he's like, I need some ergodic supplies. And the manager says, okay. Trash orders a bunch of alcohol and gets drunk in the field.
Just walk around in my backyard.
That's a way to learn physics.
Gonna get so ergodic right now?
Listen, bro, you want to get ergodic this weekend?
I'm impinging all the points in a given space. All right.
I don't have any other
everything
questions.
we need to know about quantum. I would just like to say that I've left with some new knowledge,
Oh,
but I'm mostly left with the same questions I've always had.
yeah.
Okay. So this technology really, because we never even got to like the fact that there's people that are throwing out terms. I've seen this happen, especially with like a lot of the clickbait, like I'm going to trick my uncle into believing something videos, which is just like, just wait until the quantum AI revolution happens. Is that, I assume that's not a real thing in any sort of capacity.
No.
And that everything they're saying is just words that are I just assume they're just two words next to each other that sound very fancy, but have no actual value or meaning. Okay.
It does seem
if
like...
you hear that, if you ever hear the word quantum talking about anybody who's not a physicist, just assume they're bullshitting you.
Okay, that's
pretty
good
much
to know.
always. Right?
So
Do you think, Ginger Bill, though, since AI is like a big matrix multiplication thing of, probability distributions, like that there could be potentially, like someday, AI, like a quantum AI chip that could
Maybe they would
stuff.
do that in the day, but I mean, anytime soon at the moment, assume it's BS.
Yeah,
is
that
what I'm
makes
saying.
sense.
And
That makes sense.
TJ, is it really just probability distributions, or hear me out? Is it just a really confusing compression algorithm?
Which one?
AI.
Yes.
It's very lossy compression
I
algorithm.
think
yeah.
it's
Very lossy compression
think,
algorithm, actually.
I think AI is. I would say it's more of a. It maps ideas into higher dimensional spaces, and then it points in certain directions towards those things. Which that's why it makes me feel more like quantum stuff, because it also has a state vector. Like, and that's why words get associated with each other, because they're near each other in the same space. But I don't work at OpenAI, so Sam Altman hasn't told me if we've achieved AGI internally or not. I'm just doing this for the love of the
Sora
game.
video. He'll tell you, don't worry. You can get
Love the
Sora
game,
video
dude.
directly him saying that already.
Yeah, true. Yes.
All right, well, I guess I'll have to tell my uncle about quantum AI being a lie. Which, by the way, is how I heard about all this. Just like, dude, what the hell is all this quantum AI business? And I'm like,
You're like,
brother, I don't understand those.
I'll
those
call
two
my-
words individually I struggle with, let alone together.
I'll call my closest thing to a quantum physicist friend, and we'll work on this together.
Oh, thank you for answering the age-old Facebook question. So that should really help.
I'll report back on my mom's wall right now. Mom, we don't have to worry.
I forgot they called it a wall. TJ, such
is
a
a
good
wall.
poll. I don't even think I could have done that.
A
Do you
poker
still have?
right
do you
now.
I've not been on Facebook in over a decade, but do you still have to like people say that what their status is and such like that or anymore, or no?
People still use that thing. I don't, but
Do they
I'm
really
logging into
still use
Facebook
it?
right now. I'm going to say on a podcast.
I did
okay.
try it. I did try, like, I logged back into Facebook because I just got so curious just to, like, see, does it still exist? And I went back there and I realized the old things that I set myself up as are still, like, what I'm defined as on Facebook.
Oh, sick.
And so it says I'm in a domestic partnership with my wife. And, what's it called? And I'm still a rocket scientist at Jesus.
Nice.
Jesus Incorporated is where I work as a
Nice.
rocket scientist.
Here you go, guys. On a podcast.
on a podcast.
Like,
Podcast. Oh right, you can still do it.
Wow.
Okay.
Dangerous
know.
game pulling up your Facebook.
I was pretty sure it was fine.
Fine.
Wow. Okay. Well,
I don't have anything on there that is cancelable. I've got lots of embarrassing posts from me and my then girlfriend, now wife from high school. Oh, I miss you so much. It's 4 p.m. Like haven't seen each other in an hour. Have to post it on each other's walls.
I haven't seen each other since your high school math class together just an hour earlier.
Yes. So
Miss you, babe. I'm in
I did-
sports class right now. I just really spiked volleyball and thought about you.
it's tough. It is painful to read. I did download my Facebook export a while ago and just poked around inside.
What is it? Just like a JSON
Cringe.
blob of stuff?
You can download everything, trash, everything, all your DMs, all your posts, everything. And let me tell you, you do not want to do that, trash. You are going to
I'm good.
think
I don't
I
wanna
look
do
like
any of
the
that.
biggest
I wanna do
loser of
that.
all time.
I want to take that and then I want to do a little fine tuning
You want to train an
Train it on
LLM.
all your
as Prime 10 years ago or
Teen-
15 years
Oh,
ago.
Teen
you can talk to
Prime.
yourself as Prime 10. Oh my
Teen Prime GPT.
Prime book.
No.
Prime book.
Yeah. Okay. Well, this has been absolutely fantastical. So thank you very much, Bill, for being on here.
Thank you.
I would say that the biggest takeaway, hopefully, everybody has is that all those posts and articles that you see all the time are just a bunch of probably just a bunch of hogwash for at least the next decade, is what it sounds like. You never know. Maybe there'll be some amazing breakthrough that will change the entire field completely. But if the field is just iterations, we're just gonna be waiting a long time until we see anything fantastic. Thank you everybody for being a part of the Stand Up Ginger Bill. As always, you are fantastic. Ginger Bill made Odin because C sucks. Check out odinlang.org.
Yeah, that's it. That's it.
.org. Okay, good.
That was like a Ron Burgundy.
Yeah, no, I couldn't remember if it's .com or .org. So
I'm
It's
Charles Barkley, and
I'm Charles Barkley, and I'm an asshole. What does he say?
I mean, .com
I'm
works
an
apparently
asshole.
as well. So yeah, .org or .com doesn't matter.
Oh, nice. You got both of them. Okay.
Yeah.
Nice. And then, of course, we have Tej. I don't know if you know who Tej is, but he produces courses for boot.dev,
I have,
boot.dev
yes.
/Tej, correct?
I would use promo code BTW for both of us.
Well, I was gonna get there. I was gonna get
Oh,
like the
okay.
old M Night Shyamalan.
With a twist.
Yep. All right, I am Prime. Of course, I'm just going in order of the boxes I see. I am Prime. I also have courses on boot.dev, boot.dev/prime. But if you like TJ and I equally, you can do boot.dev/by-the-way for 25% off, and both TJ and I will get paid. Lastly, we have with us Trash Dev. Trash Dev, I don't have anything I can promote of you other than your Twitter. Go check out Trash's Twitter where he will promote anything and everything. So just slide a DM and be like, hey,
Hit
you
me
got a
up.
cryptocurrency?
I'm a cheap
Hit him. He'll shill
cheap
that.
guy.
He
got
works for
snacks?
Yum Earths, buddy.
Yeah.
Send him some Yum Earths.
I'm
and he'll be
seeking
happy.
food sponsorships. Like seriously, I
Will-
think that's my
Will-
next calling. Not even kidding.
I honestly
Will
think
shill
that's such
for
a good idea.
food.
Yeah.
I will
met-
let you have a food sponsorship on this podcast ad infinitum with no money attempted to grab into it. If you can bring in
Yes.
your own,
Completely separate. Bring your own sponsor. BYOS.
I'm in those DMs.
Make
don't
sure
worry.
it's human food sponsorship as well.
Yeah.
Okay.
No bully sticks and stuff.
No bully sticks, exactly.
No,
I don't
you
think that
can.
intro made it onto the recording, so
this is-
they're not
people
going to
have no
they're
idea
not
what
going
we're
to know
talking
why
about
that's
at
a
this
joke.
point. It's great.
They're just gonna
Trash
hear that and be
those
like,
bully sticks.
oh.
All right. Thank you very much for joining us. This is The Stand-Up.
Bye, everybody.
Boot up today. Vibe coding errors on my screen. Terminal coffee in hand. Living